Hello everybody. In this course, so far you have learned how to determine stresses and strain in the bituminous pavement using a design charts. Now, we will do the same thing using a software called Kenpave. In a Kenpave software, there is a module called Kenlayer. So this Kenlayer is used for determining stresses and strain in the bituminous pavement. So we will see how to use a Kenlayer for the analysis purpose. So this is going to be the outline of the presentations. So first we will install the software. Once we install it, we will see a general demo on a software so that we will get familiarized with the terminologies used in determining the stresses and strains. Once we familiarize with all the terminologies, we will solve few numericals on 2-layered system and a 3-layered system using different axial configurations. So further, after understanding all the features of a Kenlayer and understanding what are the results we get it, we will consolidate all our learnings here so that we can use these further this learnings further when we do a payment design. So this is a link for downloading a software. This is an open source software. You can download it and you can install the software using a setup file in the folder. After an installation, once you open a Kenpave software, the main screen of a Kenpave software looks something like this. So in this main screen, you can see two modules here. One is corresponding to a asphalt pavement and second is corresponding to the concrete pavement. So in asphalt pavement, we are interested in the asphalt pavement module. So if you can see this asphalt pavement module, the program main button is named as a Kenlayer. That is why we call it as a Kenlayer software here. So we are going to now focus only on the half part of a software which corresponds to an analysis of stresses and strain in the bituminous concrete pavement. So all the numericals solved are from this reference, Pavement Analysis and Design by Huang. So I hope all of you are now aware of this software. And Professor Murli sir already introduced this software to you and he already explained about the principle behind the determination of stresses and strain, and he explained about the superposition concept in when you have a dual wheel load or a multiple wheels. You now know what is the principle behind determining stresses and strain. So I am directly going to start a demo on the software. So before we see the screen of a software, we will just consolidate what are the inputs and outputs you are going to get it from the software. So when we start with the demo, you can group the type of input based in this category. So first input is on the structure of pavement. So you define the structure of pavement using number of layers and thickness of each layer. So you need a thickness of each layer and number of layer. So giving this, you can define what the structure of pavement exactly is. Followed by, you have a material properties. You know it is a linear elastic theory. So to determine a stresses and strain in the linear elastic layers, you need the elastic modulus of different layer and you need a Poisson's ratio of each layer. So further, to tell what exactly the load that is acting on a structure, you know it is going to be a wheel load. So to define what exact wheel load is acting on the structure, these are the data you need it. So first we will see what is axial type. You know there are 4 types of axial configuration. Single axial, single wheel, which looks something like this. Only one wheel on one side, and axial is also only one axial. So or it can be a single axial dual wheel. So 2 wheels on each sides, which is spaced at some distance between 2 wheels, but you have only one axial. So in a tandem axial, so you have 2 axials, so 4 wheels on each sides. So this is kind of a tandem axial. So now to define this wheel position exactly, you may be needing distance, center to center distance between 2 wheels and center to center distance between 2 axial. Similarly, if you have a tridem axial, you will have another 2 wheels added to this. So you have 4 different types of axial configurations. So when for determining stresses and strain, you can use any of these load configuration, because all these loads are common in a pavement. So you can use any of these loads as required and determine stresses and strains in the critical locations. So you need what type of axial we are going to use, and you need to define the dimensions here. So in addition to distance between a 2 wheels and distance between a 2 axial, you also need what is the magnitude of load that is going to act on a pavement. So the magnitude of load is defined here using a contact radius and contact pressure. So we assume that the wheel load is distributed to a pavement as a uniformly in a circular pattern. So what is the contact pressure followed by what is the contact radius. So by defining these two parameters, you can exactly define what is the load that is going to act on a pavement. And finally, locations of stresses and strain, where exactly you need to determine stresses and strain. So you need to give depth, at which depth you need stresses and strain. Do you need it at the surface of the pavement, or at the interface of a 2 layers, or middle of some of the layers? So you need to define the depth. Depth is referenced from the top surface. So 0 at the surface. So when you go down, it increases. So you need a depth. And if you are putting it in terms of a radial distance, so what is the radial distance from the center of loading? Generally, if it is single axial single wheel, the plan looks like this. We assume it to be circular. The center point of a loading is considered as a 0 point. So if it is a other than single axial, if you have a single axial dual wheel, so you have 2 wheels. So center is defined from the center of one loading. So in such case, you need x coordinate and y coordinate. So this direction is y and this direction is defined as x. So you can define, in addition to depth, x and y coordinates to tell what locations you need to determine stresses and strains. So these are the 4 groups of input we need to give it in a software to determine stresses and strains. So now what is the output? You get it. So you all know that we need stresses and strain. So output will be 3 normal stresses and shear stress in case if it is a single axial single wheel. So in case of a single axial single wheel, the critical location is exactly at the center. You know that place the shear stress is 0. So the normal stress itself will be the principal stresses and principal strain. So if the load is different from a single axial, so if you have 2 tires, 4 tires, or 6 tires, then the principal stress is going to be the critical stress, and you need to determine principal stress from the 3 normal stresses and a shear stress value. So and for the design purpose, we will be using principal stresses and strain. So you will also get displacement along with the stresses and strain. So this is the output what we will get it from the Kenlayer software. Now let us go to the software and we will see the demo of the software. So this is the main screen of a software. We are going to use a Kenlayer portion of a Kenpipe software. So let us open a Kenlayer input. We call it as a layer input. So if you open a layer input, you can see a file here. You can use a new file. So before the new file gets saved, it will be named as an untitled. We will save it after we give all the input here. So let us go to the general input. So in a general input, the first is going to be the type of material. So before we see the input related to the payment structure, let us title it. I will title it as NPTEL. So now we need to give what type of material it is. Here if you focus on what type of material we are going to use, see you have 1 for a linear, 2 for non-linear, you need to assign 3 for viscoelastic material and 4 for a combined behavior. See, you know that whatever stresses and strain we are determining here, we started with, we are going to use a linear elastic theory for this. So, you can assign 1 for the linear elastic theory. Let us not worry about a nonlinear behavior, viscoelastic behavior, or a combination of any of this in this case now. So, once we give a type of material, so whether to perform a damage analysis or not is something we need to define here. As of now, we have not learnt about a damage analysis. So, once we learn a theory behind a damage analysis, we will come back to this. So, as of now, we will keep a damage analysis to be 0, followed by you have an input for number of periods per year. This is something that facilitate us to define a different modulus for different month. For example, if you take a subgrade layer, you have a different modulus of a subgrade layer for every month. That is, in a month of, in a winter you have different modulus value, in a summer you have a different modulus value. So this allows us to define different modulus for different period. So you can go up to maximum of 12, that is one modulus per month in a year. So as of now, we will give only one modulus, and we assume that the modulus value is going to be constant throughout an year. So here the number is going to be 1. Number of load groups. See, this is the place where you define how many number of axial is going to is the payment going to get subjected to. It is not based on the load intensity, it is based on the axial configurations, and in case if the contact area is different, you can use different load groups. In case if a contact pressure is different, you can use different load groups, but you have a constraint here. You have a the number of load groups to be defined is limited. You can just read through the help menu available here and find out what is the number of load group we can define. It is generally 12 numbers, but you can always use the help menu here to understand what exactly these terms are. So followed by number of load groups, you have tolerance for numerical integrations. So as of now, the default value of a tolerance, which is 0.001, is given. So let us stick to the default value. So this tolerance is to terminate the program, this tolerance value is used. So when you run a program, we get the results based on a numerical integration. So when the integration converges, this is the tolerance value it uses. Number of layers. Here, let us use a 2-layer system or 3-layer system. So for the demo purpose, I will give this number to be 3. Number of Z coordinate for an analysis. So this Z coordinate is a depth. So it at what depth you need the stresses and strain value. So you can, this is just, you need to define a number here. What exact depth you can give it later. So let me give 2 numbers. It indicates that at 2 different depth I need stresses and strain. Maximum cycle for numerical integration. So now tells you what number of integrations you have to go for. So here let us stick to the default value, and we will see how many integrations the software has used for converging the result later when we see the result from the software. So type of response, you can use 1 for displacement, 5 for displacement and stress, 9 for displacement, stresses and strain. Let us give 9 here so that we see all 3 values. All layer interface are bonded. So we give this bonded is 1, unbonded is 0. So you know we are going to look into the bonded layer. So it is 1. Number of layer for bottom tension and top compression. We will revisit this when we do a damage analysis. So as of now, we will keep it as a default number. In system of units, let us follow SI system. So I will give this 1. So this is a general input. Once you complete the general input, you will have a status updated here as done. Now go to Z coordinate. So you see, we have given 2 depth, 2 point where we need to determine stresses and strain. So you have 2 points here. You can give at what exact depth you need to find the stress and strain here. let me give some number, but it has to be given in centimeters. So I will assume the first layer thickness to be 100 mm, so I give 10 centimeters, and I'll assume the second layer thickness to be 20 centimeters, so I'll give 10 plus 20, that is 30 centimeters. So once done, so next is layer input. So in the layer input, you have Poisson's ratio and thickness of different layer. We assumed a 3-layer structure. We need to give a layer input for 2 layers, and third layer, that is a subgrade layer, is considered as an infinite layer. So first thickness of first layer is 10 centimeter, thickness of second layer will take it as 20 centimeters. So you can define a Poisson's ratio here. So let me give a Poisson's ratio value of 0.5 for each layer. So you know asphalt, you can take it as asphalt layer, you can take it as 0.35, and soil layer somewhere from 0.35 to 0.5. See, there is also another column hidden here, kilonewton per meter cube, which defines a density, and we don't need this number here, that's why it is hidden. We are doing only the linear elastic analysis. Once we define a layer input, the next one is an interface. See, we have given an interface to be bonded, and hence there is nothing to change in this. Next is a moduli input. So when you go to moduli input, as we have seen before, you can give an input for 12 different period. So you have 12 different provisions here. Now we have given only one in that. So we have only period 1 is highlighted. So now we have 3 layers. You can define modulus of 3 layers in terms of kilopascal. So let me give the modulus of first layer to be 10 power 6 kilopascal, modulus of second layer to be 10 power 4 kilopascal, and third layer to be 100 kilopascal, 100 or 1000 kilopascal. So I am just taking an arbitrary number here. So we will use a specific number when we solve a numerical problem. So once the moduli input is done, next you can move to a load input. Now when you open a load input, the first input which you have to look into is axial configurations. So axial configuration is defined in this load column. So if we assign 0 for defining single axial single wheel, 1 for defining single axial dual wheel, 2 for defining tandem axial, and 3 for tridem axial. Here let us use 0 for the demo purpose, which says that it is a single axial single wheel. So you can define a contact radius here. Let us use 100 millimeter or 10 centimeter here for the demo purpose. I am just picking some arbitrary number here. Contact pressure in kilopascal, maybe 500 kilopascal. So YW and XW are a distance that defines a distance between two wheels and distance between two axial. Since it is only one wheel here as of now, for 0 category of a load, this YW and XW are 0. NR or NPT is a number of radial distance or lateral points where you need to determine stresses and strain. So if I define this to be 2, so when you click on this, you will have 2 points to define. So 0 is exactly at the center of loading. You can give any number of points here. Now let us give 2 to be on the periphery. So we have taken a radius value to be 10 centimeters. So I will give the second point to be 10 centimeters, and once we have done, so our load input is done. So our load input is done. Non-linear viscoelastic analysis and damage analysis are something we are not going to do it. So it is by default, it is hidden and we cannot give any input here. So once this is done, you can just save as. So I will save it in name of NPTEL. Just save it. So now you can see that the file name is replaced to NPTEL_1. So once we complete all the input, you can come out of it and you can compile it using this Kenlayer option. So this is what I was saying. So if you get this kind of an information, means the program is completed, and you can see that complete layer routines with integration cycles, it took 11 number of cycles. So we have given 80, 80 is a default value and we kept it to be the same. It took 11 cycles for a results to get converged for a given number of tolerance value. So once you have done, you can just go to layer, L graph, and you can see the input in terms of a graphical representation. The top sketches for a plan and the bottom sketches for the section. So you can see we have given single axial single wheel. The center point is exactly at the 0. This is has a contact radius of 10 centimeters and contact pressure of 500 kilopascal. And we have defined 3 layer system, thickness of different layer, modulus value and Poisson's ratio value used for different layers are given in this. This is a diagrammatic representation of our input. So once you compile it, you can see the result through editor option. So you can go open a file. The file will be saved in doc.txt format. This is a file which we have given. When I open this editor file, first you will see all the inputs whatever you have given, and the results will be in for any given radial distance, for any given vertical coordinates, what is the vertical displacement, what is the stress and strain value. So in stresses and strain value, you have vertical stress, radial stress, tangential stress and shear stress. So for a 0 shear stress is exactly at a point where the radial distance is 0, and if on this periphery you have a small amount of shear stresses and shear strains here. So you can identify which stress is critical at which locations from this table.